topic is very interesting. It's interesting because of the intuition that comes from, for me, as an experiment that Galton did a long time ago, and that I find interesting for using ensembles is the interesting social experiment that he did in that agrarian area of late 80s. If you go to cattle market, you need to hire a consultant to make a good deal on buying a cow or ox, but he experimented that the consultant's opinion about the price of an ox would cost you, but it would be very near to the actual price. In the same direction, if he asked many common people, naive people, who know nothing about the ox business, just have heard it from here and there, and average their opinion, then their opinion is very much closer to the real price as much as the consultants. So same thing we can bring into machine learning. We have complex, monolithic, large classifiers or regressors that are trained on maybe millions of rows that learn from hundreds of features. The monolithic machine will run the risk of either overfitting or underfitting. We never know until we hit the future. But if there is a way that we can use simpler but many machines and average their estimate or prediction, somehow theoretically we are safe from running the risk of underfitting and overfitting. We will see how theory holds, and in practice you will see ensemble methods are very competitive. If you read machine learning papers, people, when they report their results, ensembles are among top performers compared to one monolithic, very smart, complicated classification or regressor machine. So if you like this intuition, we may look at the reasons. Let's start from the simple but nonlinear classifier, which is decision tree. A big decision tree will bring us what? Many decision nodes, internal nodes. The larger it is, the higher the accuracy will be, the more information it will consume. Decision trees are better in another sense because they are tolerant to missing values. They don't need a whole vector. At the same time, few of the variables in the training data may be sufficient for a decision tree. And then they are tolerant to missing values. At the same time, they can handle mixed data types, categorical and numeric at the same time, which is a cool thing. And thirdly, we see that they are very conducive for us to consume and reason about. Their open box, not a black box, as long as they are small enough. But if they are not small, the one that we are looking at, it's a tree is larger than this, deeper than this. We have only 5 levels. If we have more than 5, 10 levels, and not just 8 or 10 decision nodes, but 20 or 30 decision nodes, it won't be consumable. It won't be comprehensible by us. In a blink of an eye, we can interpret what's going on. So that larger the tree is, the deeper we go on the levels. What will happen? So the nodes that we have at the top, they are the largest splits. The root is the largest split. It splits data into 2 big chunks. In the next level, the next big possible chunks. And the deeper we go, the smaller the data is being divided into the next nodes. So at the end, near the leaves, if the tree is deeper than this one, we know we will see very little of the training data at that level, and which means we are overfitting or memorizing the data when we have very few samples to split on. Now, overfitting has an implication, 2 kinds of implications, 2 things that we don't like. Number one, we don't like error, right? Bias, we will call it, the difference between actual truth value and the predicted value. Number 2, we don't like, that is the variance in performance. So with one day, the classifier performs very well. The next day it performs very bad. And the next day even worse. And then the following, it comes closer to the ground truth. So that variance in performance is the second negative that we want to reduce. So a textbook explanation of looking at the error at training and test time is explained by these 2 curves. In practical problems, we don't have this much smoother curves, error curves. As the on x-axis model complexity increases, the error on training data decreases, the blue line. And the more, in case of, let's say, decision tree, the more the nodes we have in the tree, more levels, we see that the decision tree, being a nonlinear classifier, will tend to perform better and better on training data until it just memorizes. And there is a decision node for every unique example in the tree, and we can produce very little error. But for the held out data, when we test the same decision tree, there is a spot after which test error starts increasing. in that particular spot, we tend to use as a heuristic for stopping to feed more data to the tree and increase the node squeeze. After that point, we want to prune the tree and use the Occam razors principle. So to the right side of that spot, we call the classifier or regressor is overfitting to the data. To the left hand, it is underfitting. So we somehow want to fall in this area. Underfitting means we need more parameters. Overfitting means we need less parameters. This is just for one model. The difficulty in AI agent or machine learning components life is that limited data. We have limited data. How can we use the available data smartly in a way that we arrange it in a way that every data point gets a chance to be tested? And we do a k-fold cross-validation where every fold is held out for each model. A, B, C, D are held out folds, and the blue ones are fed to the machine for training. And we see that for every experiment or every fold, the output measured as accuracy or RMSE is written here. Before doing this, we shuffle the data so that we can ensure IID. I have a question here. When we run the k-fold cross-validation, k is 4 here. There will be how many models that we are training?
I'm a bit confused by the question. What do you mean by the number of models? I mean, you're taking 3/4 of the data, right, and using that as training, and then the last quarter you're using for the testing.
Right. So how many models will be trained in this four-fold cross-validation setup?
No, because you're taking the last quarter of the data as validation, right? You're doing that 4 different times.
4 different times, 4 models, right?
Yeah.
And then what we do what? We have 4 models. How do we spend the rest of the life for? I mean, what should be the next question? Next question should be which one of them to be used in deployment, right? When we move to that question, before moving on, we need to check something. And that something is that the score for each model, they are uniformly distributed. They are in the same neighborhood. They are not having high variance. If one of them, let's say the 4th one, is 54, then we cannot go to the next step and select one of the models randomly. We need to fix something. That something is there is something wrong with the D, this part of the data. There are some more difficult examples here, or data is not truly IIT, or whatever is the reason. So model 4 is giving 54 RMSE, so it is much better than the others. So what happened here? Why others are not also in the same neighborhood? We usually use statistical methods like ANOVA to find out if the difference between the results is not by chance or not by design. So after we make sure that they are in the same neighborhood, how do we average? Like pick one, or we can average like this. A common confusion is that we average models like 2 models, M1, B1, M2, B2 for 2 lines. We can average them, which is incorrect. We just randomly, if all are in the same neighborhood, we pick one of them randomly because all others will perform in the same way in future. So we just pick one. We agree on that, right?
I mean, if they're all in the same neighborhood, I don't see a gap in performance. But then I also, I mean, if you just chose the one where they gave the best RMSD, right, then you'd be picking up on whatever kind of weird biases it has. So maybe it still is better to do the random selection there. Yeah.
If one of them is outstanding, we cannot move to the selection part. That is my point. We need to fix the reason why one is outstanding or 2, or as long as the ANOVA test is, don't let us go to the next step. We stay here and fix our problem.
Right. That's fine. Yeah, I agree that if they're all around the same, you can just go with whichever.
All right. So for each fold, let's depict the accuracy or RMSE using these black diamonds. There could be 4 different situations. The star is the ground truth that we are trying to reach. And in situation 1, the score from each fold is depicted like this. So we can see there is high variance. And the difference between star and the average of these points, bias, is high. So high variance and high bias. In the second case, the variance is small, but the difference between star or the target ground truth and the prediction is still high. So the high bias, second situation, low variance, we want to avoid that. Low bias is situation third, but still we have high variance. We don't want that. In fourth of this quadrant is low variance, low bias. So we want this situation as long as we hit the target in low variance for all possible settings of the experiment, we are good. Interestingly, bias and variance are like opposite sides of magnet. When we try to control bias, variance goes high. When we try to reduce variance, bias goes high. So there is a trade-off, bias-variance trade-off, similar to the previous slide in training and test error. We want to find a sweet spot. We need to find a balance between bias and variance where one is not overshadowing the other. Right, we reduce, the best situation would be both are reducing, but in practice, once we try to reduce variance, we'll see the biases going higher. And when we try to reduce bias, the variance starts going higher because of overfitting or underfitting. Before we were working with the parameters of the machine itself. Now we have another layer of parameters. We are going to call them hyperparameters that will be controlled by us. And that is an art. Again, that is heuristic. So we will learn how we do that. But first, we want to make sure that what we are saying of putting many naive learners against one big, complex, monolithic learner, does it make sense? And if it does, why it makes sense and how we can do that. And that is all there is for ensemble learning. So bias and variance are the two measures, two challenges that we try to tackle in machine learning. We will see how many naive learners can do that better. So data is scarce. On the testing strategy, we can split and make the data look more and make our test sounder so that every example gets a chance to be tested on the model. And we now want to extend that. Any idea, we want to inflate the data. We want to make the data look like more than it is. There are 100 examples. Can we make them 1,000 without introducing new data? One simple method would be to sample with replacement. Sampling with replacement 10 times can, let's say, or 20 times, we sample 50 samples from the total 100 and then train a model, and another 50, train another model, another 50, train another model, and repeat that 20 times. So we inflate the data, right? Artificially, somehow we present it to the classifier in a way that it's 1,000 examples, not 100. But if we do that, what do we lose? What do we have to lose there?
Professor, I have a question regarding this. It might not be the answer. So it's like if we are using the same data repeatedly to train the given model, won't it be losing new cases? Like say if we are having 50 samples of data and in the new 51st sample, there might be a new logic for the classifier. So won't the model be losing his credibility for going on the classifier and giving us the correct result?
For every new sample data, we will have a separate classifier, not the same one. So we have, if we sample 50 times or 100 times, we are training 100 different separate classifiers in every classifier is looking at only that particular sample.
Okay.
And that sample is not systematic. We randomly sample 20% or 30% of the data, but machine, well, let's say we are using SVM or a neural network or naive Bayes or decision tree. There are 20 decision trees. In that case, algorithm is same, but the incoming data is different. So the number of classifiers will be naive, maybe in the sense that they will see individually less data points compared to the one that sees everything. But from the input point of view, we have inflated data. We have made 100 examples, 1,000 examples by sampling with replacement. So if we do that, what do we lose? The sampling is with replacement, which means that same example can go to
across multiple.
Yeah, same example can go to different data sets.
That same bias in the data can be spread across multiple.
Yeah, exactly. And we say that many of our classifiers are relying on IID assumption. They are identically independently distributed. So once we do with replacement, that means we are allowing same examples or same 2 or 3 examples to be going into the training data, which will violate that assumption. But we swallow that pill because the benefits are more. So pictorially, we see the whole data set here. We sample into n with replacement. So there can be duplicates. So we sacrifice IID. And for each sample, we train a separate classifier. And then if it's a regression problem, they are regressors, we just average. If they are classifiers, we do winner takes all, which means we take a vote. So if there are 4, so 3 should give same opinion. Or if there are 5, 3 out of 2. If there are 6, 7, 8, majority takes all. This particular setup is based on bootstrapped samples, and at the end we are doing aggregation. So as a whole, this ensemble learning framework is called bootstrapped aggregation or backing. Here we are working on the rows. So we take all the features in each row and sample rows it many times. The 20% of the rows of the data are sampled and then classifier is trained, and then another 20%, another 20%. After sampling, we put them back. So 2 different samples may have some portion of same examples. And that finally will, since the performance is being aggregated or majority vote taken, so we lose IID there. Now they are not identically distributed. But given that violation of our assumption, based on this analogy of Ox estimation by many naive people and one expert, this setup works better than one monolithic big decision tree, because the decision tree coming out of 20% of the data is bound to be smaller than the original decision tree produced by the whole 100% example. Simpler decision tree is bound to make some mistakes, but that mistake will be averaged by many other tens of other decision trees or hundreds of other decision trees. So average of all those simpler classifiers trained on subset of the data is competitive to one monolithic one. Monolithic will run the risk of overfitting. The smaller ones run the risk of underfitting, but they are competitive and they're simpler to learn, and they will be somehow, not always, but sometimes better than the monolithic one. There is a concept of stability of machines in physics where we give an input and we know the expected output. If we change the input slightly and the output changes drastically, we say that the machine is not stable. The medium is not stable. In machine learning, there are some experiments for beating the machines. So some deep learning models can detect images very successfully, but for adversarial verification of the correctness of those machines, people found out that when we change a little bit in the input, the output changes drastically. So for fish detector machine which can detect fish in the images, if we replace eyes of the fish, it cannot detect. So a small change in the input, if it changes the output drastically, we say the classifier is unstable. So decision trees are one example of such learners that can have drastically different output if the input is changed, because if you visualize a decision tree with 2 nodes, it will be like a cross, 2 splits on X and Y, 2 features X and Y, and 2 splits will make a cross on the 2D plane. And on those splits, on the values on the borderline can change the class, right? So the decision trees are not stable learners in that sense. So they are not stable. That's why overfitting causes decision trees to have unstable output, and showing them less data is going to have stable decision trees. Maybe we will see. But there's going to be another helping strategy where bootstrap aggregation is not enough. We will look at that. But for bootstrap aggregation, we have many interesting other applications as well. For example, other than the training data is small, we have class imbalance problem where a minority class is 1% of the samples, or 5 or 2%. In majority class overshadows the minority. So if we sample, the problem will be even worse, right? We've sampled 20% of the data, but now our sampling will be class conditional. We will inflate the samples from minority class to be represented in the sample data with higher proportion so that the classifier can see it more. So that if we allow that class conditional bootstrap sampling, we can meet this challenge of class imbalance. So there are some sampling algorithms that do this for us. Undersampling the majority class is take less samples from majority because they are already 99%, more samples from minority. Oversampling the minority class, For that, we have a strategy of creating synthetic samples that are not in the training data, but they are in the neighborhood. So we generate synthetic samples to inflate the proportion of minority class, or we undersample the majority class using bagging, or we can modify the cost function. If we make a mistake on minority class, the cost is more. If we make a mistake on majority class, cost is less. So the cost function is modified so that we can somehow find a boundary or a regressor which is not ignoring minority class only because it has fewer samples. So combined, all three, undersampling, oversampling, and modified class function, cost function, give us a way to cope the class imbalance problem. So even though it is not guaranteed that bootstrap sampling will always produce many naive learners that can compete with one monolithic, but they can sometimes compete. At the same time, bootstrap sampling allow us to meet the challenge of class imbalance. The next dimension that we can work on is the feature dimension. In the bootstrap, we have this dimension. We sampled rows with replacement, created many different data sets. Now, if we want to work on the features, after doing bootstrap sampling, we don't use all the features to train a classifier. We can again randomly sample among the features. Out of 200, every time we pick randomly 20 or 10% of the features. So sampled rows and then sampled features, we train a classifier, go back again, sample rows and sample features, train the classifier. And for all the classifiers that are trained in this way, we can now have even simpler classifiers, but they are going to be better than one monolithic ones because they won't run the risk of now overfitting. And secondly, we find a side product of this setup or this framework. They refer to this as boosting. So bootstrap sampling, in addition, boosting. Boosting gives us freedom from k-fold cross-validation. So the k-fold cross-validation is a setup where make sure that every sample gets its chance to be tested on the classification algorithm. So the out-of-bag error is less and less. But when we do this procedure of bootstrap sampling and then sampling the features and then training, we are already making sure that out-of-bag error is less and less. So we don't have to do k-fold cross-validation in this case because it is already validated. The interesting name that we have for this kind of setup coming out of these boosting and bagging frameworks is random forest, because instead of one big monolithic tree, we have many small trees. Now, in order to train a random forest, in case of decision tree, we are working on information gain and split of the data into folds, and then what portion of the training data will go to come from which class, those parameters. And we also look at the number of nodes that we can allow in a decision tree. But when we train a random forest, we have parameters like how many decision trees we want in an ensemble. So the algorithm will need to know, do we want 200, do we want 300, and both will give slightly different performance. So the either grid search of the parameters or random search. So we, instead of in a grid of possible hyperparameters, we check every cell, we randomly pick different cells and try to find the point that takes us closer to the out-of-bag error, just least OOB or OOB error. We also use number of sampled features as parameter. Maximum depth allowed. So when we are after bootstrapping samples, after sampling the features, when we train a tree, decision tree, with reduced samples and features, we use a parameter that stop training the decision tree when there are, let's say, 10 or 20 samples at the bottom node, at the last node. If we run that threshold, we don't want to split anymore because it will overfit after that much splitting. So we can control the depth of the tree by number of sampled features, maximum depth parameter, and out of back error, we can mention that once it reaches RMSE, let's say 10, then we want to stop. Beyond that point, if we train more, it will overfit. So these kind of parameters, we call them hyperparameters, and we search for them. So there is going to be another algorithm that is going to train the ensemble using these parameters. In that algorithm will use these hyperparameters to go further, train individual naive classifiers. But this is the story for today, which is compared to the previous modules that we did, is very less mathematical or calculus here, more intuitive. So the higher the number of naive learners or estimators we have, the less overfitting we will have, and the average performance of those naive smaller trees will beat one big decision tree. That is the intuition, and that is all there is for today's story.